All right, last video on inverse trig. At first glance, the examples that you see in this video are going to look really similar to the examples that you saw in the previous video. However, if you look a little bit closer, you might notice that in the previous video, the inverse trig function was always on the outside of this function composition, whereas in this video, the inverse trig function is always on the inside of the function composition. And it'll turn out that when the inverse trig function is on the inside, you have a little bit more flexibility in terms of how you solve them. Let me show you what I mean. This first question is asking what is the sign of the arc cosine of 1/2? Well, the first way you could attack this is just like you did in the previous video. You could work from the inside out. So you could ask yourself, what is the arc cosine of 1/2? Remember, this is asking for an angle. And the restriction on that angle, because we're talking about arc cosine, is between 0 and pi. So you're thinking about the top half of your unit circle. And you want an angle so that when you take the cosine of that angle, you get 1/2 as your answer. Well, if you remember that the cosine of an angle is just the x-coordinate, maybe you'd be able to see that the 2 points on your unit circle where the x-coordinate equals 1/2 are up here and up here. But in order to stay up on the top half of our unit circle, we must be talking about this point. We want to refer to this angle as something between 0 and pi, so we'll measure it this way and get pi over 3. Because the x-coordinate here is 1/2 and pi over 3 is between 0 and pi, the arc cosine of 1/2 is equal to pi over 3. So if the arc cosine of 1/2 is pi over 3, I can replace this arc cosine of 1/2 in the parentheses with the pi over 3. And now this question gets really easy. What's the sine of pi over 3? Man, that's going back to when I first learned my unit circle. Pi over 3, oh, it's already labeled. How convenient. Sine, that's just asking for the y-coordinate. The y-coordinate is root 3 over 2. My answer is the square root of 3 over 2. And so maybe you're like, all right, I got the hang of these. This is easy. Then we move on to the next one. Tangent of arc sine of 3/5. Let's see, arc sine, I'm thinking about the right side of my unit circle here. I want an angle between negative pi over 2 and pi over 2. And I want the sine of that angle to be equal to 3/5. I don't remember ever getting the sine of an angle being equal to 3/5. Where's the y-coordinate equal to 3/5? I have no idea. That's not one of the memorized values on my unit circle. Dang, that's a bummer. He must have messed up and gave me an impossible problem. Actually, no. You can solve this problem. When the inverse trig function is on the inside of this function composition, there's methods you can use to solve it. And maybe I can demonstrate a method by redoing this problem a different way and getting the same answer. Rather than thinking about this question in terms of my unit circle, what you can do is draw a picture and think about this in terms of triangles. A way that I think you'll prefer to solve this problem is what I'm going to call the drawing triangles method. And the drawing triangles method is a 4-step process. You use it anytime your inverse trig function is nested inside of a trig function. First step is you're going to replace that inverse trig function, which remember has to be on the inside, with the letter t. And when you do that substitution, you actually write it out. You say let t equal whatever you have inside the parentheses. So in this case, the arc cosine of 1/2. What we're going to end up with are 2 columns going down here, so that'll be kind of tricky. But the first step is we're just going to call the thing that's inside the parentheses the letter t. And if I'm calling this thing inside the parentheses the letter t, then this thing is just equal to the sine of t. Note 2 different columns here. The right column is going to be my answer. You're like, it doesn't seem like we've done anything. I'm confused. What's going on here? Well, just have faith. That's the end of the first step. Don't worry about why you're doing it, but you can do it, right? You can take whatever's inside the parentheses, say that that's equal to t, and then replace whatever's inside the parentheses with a t in your second column. Yeah, I guess. Okay, good. Step 2. The best I can do for step 2 to try to make it as general as possible is say what you're going to do is you're going to take this equation that you just wrote from step 1, where you have the inverse trig of some argument equals some angle t, and you're going to solve that for whatever this argument is. That sounds really complicated. It's not. It's super easy. We have written that t is equal to the arc cosine of 1/2. What that means is that the cosine of t is equal to 1/2. Because cosine and arc cosine are inverse functions, all I have to do to switch from arc cosine to cosine is switch the inputs and the outputs. Instead of having 1/2 as the input and t as the output up here, I'm going to have t as the input and 1/2 as the output. All I'm saying is rewrite this equation as this equation. Simple. What you're going to do in step 3 is use that equation that you just wrote in step 2 to draw a triangle. And you're like, what do you mean to draw a triangle? Think SOHCAHTOA. So it's been a little while since we've done this, but at some point in the class, I think you were able to take equations like cosine of t equals 1/2 and use that to draw a triangle. What you did is you always made a right triangle, and I typically oriented them so that our angle, t in this case, was down in the bottom left. And then you said, wait a minute, SOHCAHTOA, cosine is adjacent over hypotenuse. So this is telling me that the ratio of the length of the adjacent side to the hypotenuse must be 1 to 2. Relative to this angle, here's adjacent, here's hypotenuse. 1 divided by 2 gives me this 1/2. And what I now have is a picture of a triangle, although really I can do a little bit better, right? Because I have two sides of a right triangle, and anytime you have two sides of a right triangle, you really have all three. If I call this third side, I don't know, b, then 1 squared plus b squared is equal to 2 squared from the Pythagorean theorem. So 1 plus b squared equals 4. So b squared is equal to 3. So b is plus or minus the square root of 3. But because I'm talking about side lengths here, it's just the positive value. So b is the square root of 3. I have this right triangle drawn here with all three sides labeled. That's the end of step 3. Step 4 is to evaluate the other column. And again, I'm going to put SOHCAHTOA down here to sort of remind you how to do that. What are you talking about the other column? Remember, the way I set this up, I had two different columns going on. I started by letting t be equal to the inverse trig function, and that changed the original question from sine of arc cosine of 1/2 to just the sine of t. My answer is the sine of t. I couldn't figure out the sine of t originally, but now that I have this beautiful picture down here, I can figure out the sine of t. I can use SOHCAHTOA. SOHCAHTOA tells me that the sine of t is the length of the opposite side divided by the length of the hypotenuse. So the sine of t would just be equal to the square root of 3 divided by 2. Square root of 3 divided by 2, hey, that's the exact same answer I got over here. How do you like that? It's kind of a weird method. It's strange having two different columns going on at the same time. But the nice thing is it's really consistent. You always do the same thing. And you're like, nah, I'm good. I like the unit circle a little bit better. Thanks, but no thanks. I'm not going to use this method. Well, for problem 1, you could do it anyway. But for the rest of the problems on this little worksheet, you could not solve it this way. Like for this problem, I couldn't start by working inside the parentheses because I don't know the arc sine of 3/5. And that's going to be a problem. No, it's not. All you got to do is let t be equal to the arc sine of 3/5. And remember, if t is the arc sine of 3/5, then this thing that I'm looking for here is really just the tangent of t. My second step says that if t is the arc sine of 3/5, then the sine of t must be equal to 3/5. My third step says if I know that the sine of t equals 3/5, I can draw a triangle, specifically a right triangle, where my angle t is down here and the lengths of the opposite side to the hypotenuse are in the ratio 3 to 5. I have two sides of a right triangle, which really means I have all three. If I call this remaining side, I don't know, a maybe, then a squared plus 3 squared has to be equal to 5 squared. So a squared plus 9 is equal to 25. How do I always run out of room here? A squared would be equal to 16. So a is equal to plus or minus 4. But since I'm talking about lengths, it must be equal to positive 4. What I'm saying is that my triangle here is a 3, 4, 5 right triangle. Oh yeah, I remember that from like a geometry class, I think. Yeah, don't worry about that. You have this triangle. You can now move to step 4, where you can answer the question. The question is, what is the tangent of t? Staring at this picture, I know tangent is opposite over adjacent, so the tangent of t is just equal to 3/4. Man, you're going really quick. I'm not sure I really follow this. Well, let's do it again. What would you do here? First step, let's let t be equal to the arctangent of 1/2. If you let t be equal to the arctangent of 1/2, then this question is really just asking me, what is the cosine of t? More on that later. If t is the arctangent of 1/2, then the tangent of t is equal to 1/2. If the tangent of t equals 1/2, I can draw a right triangle. Tangent is opposite over adjacent, so this is 1 and this is 2. I can solve for this side length because I know this squared plus this squared equals this squared. So 1 squared plus 2 squared is 1 plus 4, which is 5. So c squared is 5, therefore c is plus or minus the square root of 5. But again, we're talking about side length, so it's the positive square root. I have all three sides of this right triangle here. It's easy enough for me to figure out cosine of t. Relative to this angle t, which I should have put in my picture, the cosine is the adjacent side divided by the hypotenuse, so it's 2 divided by the square root of 5. Leave your answer like that and you're probably fine, but technically you should rationalize the denominator, so you should multiply the top and the bottom by the square root of 5 to get 2 root 5 over 5 as your answer. Let's do it again. Oh, this one's totally different. Here, I'm not even taking the arctangent of some number. It's of some expression with a's and b's in it. I bet this is going to be super hard. Nah, same method will work. We're going to start out by letting t be equal to the inverse trig function that's inside the parentheses. So in this case, the arctangent of a divided by b. Okay, that's weird, but I guess if I'm letting t be equal to the arctangent of a over b, then this question is really just asking me what is the sine of t. More on that later. If t is the arctangent of a over b, well then the tangent of t must be equal to a over b. If the tangent of t is equal to a over b, I suppose I could draw a triangle. I'd throw the t down here, I'd make this a right triangle, and I'd say that the length opposite this angle divided by the length adjacent to this angle, that's the TOA of SOHCAHTOA, is in the ratio a over b. So I'd throw my a over here and my b over here. And then I'd have to solve for the hypotenuse, maybe c. I would say that a squared for this one plus b squared for this one must be equal to c squared. To solve this equation for c, just take the square root of both sides. C would be the square root of a squared plus b squared. It's a weird looking triangle this time. It's not quite as pretty as it was before when I had numbers in place of all the different side lengths, but it'll do. I want to figure out the sine of t, no problem. Come down here and remember sine is opposite over hypotenuse. So in this case, it would be a divided by the square root of a squared plus b squared. When there are expressions like this, just with letters floating around, frankly, I'm fine. You don't have to rationalize the denominator here, but I should at least show you how in case you wanted to. You could multiply the top and the bottom by the square root of a squared plus b squared, and now that would appear up on the top. And on the bottom, I'd have the square root of a squared plus b squared times the square root of a squared plus b squared. Those two square roots would cancel out, and I'd be left with a squared plus b squared down in the denominator as my final answer. One last time, cosine of arcsine of x, again with the letters floating around here. Although now the letters don't form a fraction, so it'll be a little bit harder to draw my picture, but not that bad. First step, just as you suspect, we're going to let t be equal to the arcsine of x. With that substitution, this question is really just asking me what is the cosine of t. More on that later. If t is the arcsine of x, then the sine of t is equal to x. That's going to be really hard to draw a triangle, because when I draw my triangle down here, which for some reason I'm making super big, and I throw t down in this corner and I say that I have a right triangle, how can I make opposite over hypotenuse just x? Don't I need this to be a fraction? Well, I guess you could write it as a fraction. You could think about x is really just x over 1, and now maybe it's easier for you to think SOHCAHTOA. The sine of this angle should be equal to the length opposite divided by the hypotenuse. So x and 1 are the length opposite and the hypotenuse respectively. And all I got to do is solve for this side length down here. Well, Pythagorean theorem tells me that a squared, if that's what I call this thing, plus x squared must be equal to 1 squared. So a squared is equal to 1 squared is just 1 minus this x squared. Take the square root of both sides, and you get a is the square root of 1 minus x squared. I could put that in my picture, and then I'll have all three sides of this right triangle labeled, which will make it really easy to get my answer. Remember, the answer is the cosine of t. Come down to your picture. Adjacent over hypotenuse would be the cosine. So it's the square root of 1 minus x squared divided by 1. And when you're dividing something by 1, you don't even have to write it. So the answer would just be the square root of 1 minus x squared. This little drawing the triangle method, at the risk of having you roll your eyes at me, is kind of fun. I really like this process, and it turns out that it's fairly useful for doing these algebraic simplifications. You don't really need it for problem 1, as we saw, and you could even get around problem 2 without doing it, and you're like, no, that'd be impossible. I don't know the arcsine of 3/5. Right, but your calculator does. With the help of a calculator, you get a decimal approximation, and you could still figure this out. But you could not figure out things like number 4 and number 5 when we just have letters floating around without doing some pretty intense algebra or using this drawing the triangle method, which I certainly prefer.